I'll start off by saying that I'm a postdoc researcher with a block research group at ETH Zurich. And what the group does is develop methods and computational tools to design and build structures more efficiently. And of course, nobody at this point in time in my presentation will stop me right there and say, why would we ever need more efficient structures? But I'll try to put it in context nonetheless. So usually when we think of climate change and what happens around us, we think of everything, but not the construction industry is not the first to come to mind. And in 2017, it was one of the biggest contributors to climate change. It is one of the greatest polluters, so it is also one of the industries that we can have an impact in. The bad news is it's not bound to get better, because by 2050, the projection is that there will be another 2.1 billion people on the planet. And whether we like it or not, we will have to build housing and infrastructure for them. So that means that we will have to build a lot. It's been likened to building one New York every month for the next 40 years. That is a lot to be built. And if we do that in the way we do now, so with the technology we have now and with the methods we have now, we will be faced with a lot more pollution, resource depletion, and a lot more waste. Luckily, it is so that today we can intelligently include structural performance in architectural geometry, and we can create these structures that are not only beautiful, they are efficient, and they use very little material. Unfortunately, when we look at how this is being done in reality, we find a system that has remained largely unchanged for the better part of 100 years. This is the 1950s or 1960s almost. What we see is that even though we've gotten better and more streamlined and more efficient at our formworks, what we need for building these concrete structures is a heavy mold that needs to be held up by a lot of scaffolding and ultimately is turned into a pile of waste. So if we want to take full advantage of the potential of these kind of structures, what we need to do is not only find better ways to design things, but we also need to find better ways to build these structures. And when it comes to building these structures, one possibility is to use a textile instead. My research looks into how we can use specifically knitted textiles. Now, textiles, regardless of whether they're knitted or not, are a lot lighter than wood. They need a lot less support and are ultimately a lot less wasteful. What you see behind me is the traditional system compared to a flexible fabric system, and what you see is that you would not need as much scaffolding or support. But the trick is that you can also not build all of the structures that you want. So it forces us to also be more efficient with the structures that we build. How this works with knitting is comparable to things that you know from your shoes or your clothes. They have the advantage of being able to be put in directly into 3D geometries and have integrated features. How it works is we start off with the design, we create a custom knit that fits that design, tension it to create the shape that we want, and then the trick is, because it's still soft, to coat it with a very thin cement paste that hardens it and makes it a rigid, lightweight formwork that can be used for concrete. One of the tricky parts here was to create a computational pipeline to automatically translate that design that you have into instructions for existing knitting machines in order to create our structures, and doing so for big structures, such as the one behind me, and not just for our shoes and clothes, which is what they're usually used for. So here's the example of a structure that we built this way last year in Mexico City. It was designed in collaboration with Zaha Hadid architects, and it's a structure that is about 6 by 6 meters and 4 meters in height. You can see that with the little human that's standing next to it. And the way we built this was using a rigid frame onto which we tensioned that textile using a cable net. The steel cable net is the main load-bearing structure in this case. But what the textile provided was logistics for where those cables needed to go in specific channels. And what it also provided were pockets to put inflatables in. Those inflatables would create cavities in the structure and become lightweight saving in the material. Now, The textile is still soft, so we did coat it with a very specifically designed cement paste. The cement paste is designed by and developed by the physical chemistry of building materials at ETH Zurich, by my colleague Lex, that we adoringly call the concrete magician. But once this is hardened, we can add the concrete, and once the concrete has cured, you can take the frame away and you're left with a structure. The balloons are also taken away, and you have this lightweight thing, but the textile stays in. And that little line that you see on the diagram there is what you see on the inside of the structure itself. In conclusion, the textile had both an aesthetic and a technical function. It needed on the one side to be beautiful, and on the other side to provide all of the logistics needed to build. So to be able to insert the cables, the balloons, to have openings, to make sure that it's looser on one side so that it inflates to the correct side and not to both sides. Both of those sides, even though they look very different, are created in one single seamless process on these machines, and that is their advantage. Now, of course, these machines are limited in their width, so the entire structure could not fit in one piece. We made 4 pieces. That is still significantly less than you would need for the 50 square meters of the doubly curved surface. What we had produced on the machine is arguably the world's largest scarf. We rolled it up and brought it to Mexico in our suitcases. We brought it in our suitcases because it's light and easy to bring there that way, but also because we're proper architects, so we finished things the night before the deadline. Once there, we unfolded everything, had the 4 pieces seamed together, and held our breath that it would be tensioned to the right shape, because for now, we didn't know if it would stretch that much. Of course, it did, thank God. That showed that our algorithms do work. And we got this lightweight formwork. And as you can see, or as if you can imagine, if you had this in normal construction, it barely has anything underneath. You can really walk and see everything. We added the balloons and then coated the concrete. Here you can see my colleague Lex. And then we were left with this beautiful Swiss chocolate. Unfortunately, that is never to be seen again. It's been covered with 3 layers of concrete, but one that is now very happily a little bit less wasteful or has some weight saving. This is how the concrete was applied, and then it was absolutely beautifully smoothened out by the incredibly crafty concrete workers. This is an impression of the structure itself. You can see a play between the hard exterior and the soft interior. What you cannot see here is that the textile is actually soft and you could push it in because it has those cavities behind it. And finally, it looked something like this, even at night. What I wanted to give as takeaway from this structure is that the formwork itself, so excluding the frame, only cost about 2,000 to 250 euros for 50 square meters. The textile weighed only 25 kilos, and we brought it there in our suitcase. It took 36 hours to knit what would have otherwise taken 750 hours to mill with traditional techniques. And considering that it only took 3.5 months from the first time we sat down to design to the finished structure, it would have been impossible to build any other way because 750 hours of milling is 3 months. And finally, just as an outlook, that machine is not singular. The beauty of it is that there are hundreds of them in factories all around the world, and all we need to do is send them the instructions. Thank you.